and welcome to our second lecture. Today we're going to be talking about labor supply, chapter 2, and this is part 1 of 3 parts. Today we're going to learn how to calculate the unemployment rate and the labor force participation, and these are based on the labor force. And the labor force consists of 2 groups, those who are employed and those who are unemployed. After that, we're going to learn the income leisure model, which reflects the trade-offs that consumers face in deciding how much or in whether to work. So the labor force includes individuals in the eligible population. In other words, those are 15 years and older, so those who are legally able to work. Note that the eligible population is also called the working age population. And they're people who participate in labor market activities, and they can be either employed or unemployed. To be considered unemployed, you must be actively seeking work. So in terms of a formula, the labor force equals those who are employed plus those who are unemployed. There's 2 key statistics that can be calculated, and that's based on the labor force. One is the unemployment rate, and that's simply the fraction of the labor force that is unemployed, and that's calculated as U divided by LF. And you have the labor force participation rate, which is the fraction of the eligible population that participates in the labor force. And this is calculated as the labor force divided by P, which is the eligible population, or in other words, the working age population. So it's the fraction of people who are eligible to work who are actually participating in the labor force. The labor force measurement relies on subjectivity and likely understates the effects of a recession. For one reason is people could leave the labor force. They could be discouraged, so they could have given up their search for work, and therefore they won't be considered to be part of the labor force, and so they won't be included in the statistics. Also, the unemployment rate doesn't capture those who are underemployed. So perhaps those who have an undergraduate degree in business who are working in a retail job. The employment rate can sometimes be a better measure of fluctuations in economic activity than the unemployment rate. So the employment rate is E divided by P, rather than taking U and dividing it by the labor force. Let's go through a numerical example. This example is for Canada in 2013. So in 2013, the total population of Canada was 35.16 million. Okay, so this box here to the left represents the total population. Okay, now what we're after here is the labor force. So the first group of people that we want to remove are those who are not legally able to work. So children under the age of 15 years old, and also people who are, for example, living on an Aboriginal reserve or the armed forces. The vast majority of the people here that we're removing are children. And so what we're left with is called the working age population, or in other words, the eligible population. Okay, so this is the working age population. Now this isn't the labor force yet, because we still want to remove people who are not participating in the labor force, such as people who are retired, people who are wealthy and don't need to work, full-time students, or discouraged workers. Okay, so in terms of a general term, we're removing people who are not willing or able to work. And so what we're left with is the labor force. So in Canada, in 2013, the labor force consisted of 19.08 million. And to get that, we've subtracted from the total population 6.49 million, and then we arrived at the working age population, and then we removed those who are not willing or able to work. And so the labor force in Canada is 19.08. So we have all we need now to calculate the unemployment rate and the participation rate. But just first, we need to break down the labor force into those who are employed and those who are unemployed. Okay, so remember I said that earlier, the labor force consists of those who are employed and unemployed, and those who are unemployed can't be discouraged workers. They have to be willing and able to work and actively seeking work as well. Okay, so the unemployment rate is calculated simply as a proportion of the labor force who are unemployed. So we're just taking the number of people who are unemployed and dividing it by the labor force, multiplying it by 100 to have it in percent. And when we do that for Canada for 2013, we're going to take the 1.55 million that are unemployed, divide it by the labor force, which is 19.08 million, and we get 8.1%. The participation rate, if you remember, is the fraction of the working age population or eligible population that are participating in the labor force. So it's the labor force as a proportion of the working age population. We multiply that by 100 and we get, for Canada in 2013, a participation rate of 66.6%. And again, this is obtained by taking the labor force here, which is 19.08, and dividing it by the working age population, which is 28.67. Here is another example for 2016 in Canada. I won't go through it here, but I put it in so that you have it in your lecture notes, so you can see another example of these terms being calculated. Okay, let's talk a little bit about trends in the labor force participation and hours of work. We'll generally look at Canada, but also look at some stats from the US as well. If we look here, we see that Canada's labor force participation rate increased quite a bit from the 70s up until the early 1990s. It fell a sizable amount between 1992 and 2000, and then it increased, and then it fell slightly over the last 5 or so years. So generally, in recent decades, the participation rate has hovered around 66%. One of the reasons that it is falling in recent years is due to the baby boomer population. And if you're not familiar with the baby boomer population, after the World War, a lot of families decided to, well, a lot of people decided to have children after the war, so there was this big bulge in the population, and now they're getting at the age of retirement, and so they're leaving the labor market. If we look at trends between men and women, there are substantial differences. In this chart here, we look at the labor force participation rates by sex in Canada from 1901 to 2011. Okay, so if we look here, in 1901, less than 20% of women participated in the labor force. And in 1901, roughly 90% of men participated in the labor force. Now, if we fast forward to 2011, we can see that the labor force participation of women has increased substantially to over 60%, and the labor force participation of men fell slightly from 90% to just over 70%. So there's been a large increase in the number of women who participate in the labor force in Canada, and similarly in the US as well. If we look at the US, we have data here from 1948 to 2016, and you can see that women who are young, 25 to 54 years old, in 1948, only 35% of them participated in the labor force. In 2016, we have over 70%. So we have similar increases, although these increases are different for different age groups. So women who are 55 years and older, the increase in the labor force participation rate didn't increase as much as those for younger women. And males, we still see in the US also this decline. But the decline seems to be a lot coming from the older males. Here is some data on labor force participation rates by sex for selected countries, and this is for 2014. So in terms of an overall labor force participation rate, Denmark and Canada are the highest. If we look at male participation rates, we see that Bangladesh is the highest, although Canada is still quite high. The lowest is in South Africa for males. And now if we look at females, the country with the highest female labor force participation rate is Denmark, and Canada comes in quite close to that as well. And the country with the lowest is Pakistan at 25.9%. Now let's look at hours of worked per week by sex. So is there a difference? So in this diagram here, we have on the bottom usual hours worked. So we have 1 to 14 hours, 15 to 29 hours, 30 to 39, 40 hours, 41 to 49, and 50 plus. So one of the key differences between men and women that you see here is that men tend to work more hours per week. So if you look at the range 1 to 14, 15 to 29, and 30 to 39, women are more likely than men to be, for these categories to be associated with their usual hours worked. But then when we go above that, so into our higher ranges here, we see that the black bar, which is for men, tends to be much higher than women. So overall, men and women tend to work different hours, with men being more likely to work longer hours. That's not to say all men or women have this trend, it's just the trend on average. The vast majority of people, as you can see from here, work between 30 and 40 hours per week, so this center range. Okay, so now let's move into our model that we're going to learn. So this is a model, it's called the income leisure model, and it's going to look at a worker's decision, or a person's decision whether to work or not, and if they've already decided to work, how much they're going to work. Okay, and it's a very useful model, as we'll see, and we know that labor is the most important and abundant factor of production. So a country's economic performance certainly depends on the willingness of its people to work. A person's discretionary time is roughly 16 hours per day, and we can decide what we want to do with that. We can either decide to work for pay to derive income for consumption, or we can have leisure. Okay, so in our model, we're just going to assume that people can either work and they're going to make money and use that for consumption, or they're going to not work. 16 hours a day that they have at their discretion can be used for also leisure. So the 16 hours per day can either be used to get income or leisure, and of course it could be any combination of that in between. In this model, we're going to use the concept of indifference curves and budget constraints. We have individuals, and their preferences are going to be represented by a utility function, and the utility function is a function of income and leisure. Okay, so U is an index that measures the level of satisfaction or happiness, which is a utility. Y is income, and L is leisure. Higher U means higher levels of utility that will make a person happier. Okay, so that's our preferences. We're going to represent preferences by indifference curves, and they show the various combination of money income and hours of leisure or work. In our diagrams, we're going to be using leisure, and so it's going to show these combinations that yield the same level of utility or happiness. So each indifference curve holds constant a certain level of happiness. Here are some characteristics of the indifference curves that we need to go over. So consumer preferences are usually northeast on the higher or highest indifference curve. So we're just saying here that indifference curves go up in a northeast direction, and as they go up, they represent higher and higher levels of utility. Indifference curves do not intersect, and we'll look at that in a moment to see why. We're also going to assume that indifference curves are negatively sloped. We're going to assume that they're convex to the origin, and so they're steeper at the left than at the right when income is high and leisure hours are relatively few. Moving down an indifference curve reflects value. When income is low, leisure hours are abundant. And indifference curves differ among individuals because of differences in tastes, preferences, or values. So let's go into a little more detail on these. So the first one is just saying that indifference curves, as we move in a northeastern direction, they represent higher and higher levels of utility. And I'm sure you've covered this in your other courses, but here we have our indifference curves. Each one represents a certain level of happiness. Along an indifference curve, an individual is indifference. That's why we call it an indifference curve, is indifferent between the things that are on the x-axis and y-axis. So this point here, for example, the person is indifferent to, say, a point here. And this point has a much higher level of income, but as we go down to this point, there's less income, but there's more leisure. So every point along an indifference curve, the person is indifferent. And higher indifference curves represent a higher level of happiness or utility. Okay, indifference curves cannot intersect. Why? Well, if they do, it leads to a contradiction. It basically doesn't make sense. So for example, if we have these two indifference curves here, and let's say they represent preferences for a single person, right? Well, if that's the case, then what we're saying here when we draw this diagram is that we're saying this person is indifferent between point A and point B. And we're also saying this person is indifferent between point A and point C. But we're also saying that point B gives more utility than point C. But we're also saying that they're indifferent. So that leads to a contradiction. So it doesn't make sense. So if you see indifference curves crossed and they're representing a single person, then something's wrong. It doesn't make sense. Of course, if these indifference curves represented different people, then of course indifference curves can cross because they're representing different people. But indifference curves for the same person cannot intersect. So 3, indifference curves are negatively sloped. So this means that if you take away some income, you must give leisure to remain indifferent. Okay, so there's an inverse relationship. And so we can see that if we go from point L to point K, and in doing so we would be taking away income, we must give a positive level of leisure. Similarly for point M and N, if we take away income, we have to give some leisure. So if it were not negatively sloped, we would be saying that if we take away income, we would also take away leisure, and that doesn't make sense. Number 4, indifference curves must be convex. So a convex indifference curve is representing preferences in such a way that for an individual who has a high level of income but very little leisure, then they will be willing to give up more income for some leisure than if they had a lot of leisure but had a very low amount of income. And this is just representing the idea of diminishing marginal utility. So up in an area here, such as L and K, a person would be willing to give up a lot of consumption for extra leisure. But if they're down here to the right, they would be willing to give up an abundance of leisure for consumption. Because they have already a lot of leisure down here, they're going to be more interested in money. For this given decrease in income, so both the distances here are exactly the same, up here the amount of leisure that would need to be given to the person to keep them in indifference is much lower than if you were down here. And so we can think of slopes of the lines tangent to the indifference curve must fall. Their absolute value must fall. Okay? And so this is a requirement. So bottom line indifference curves need to be convex. So moving along, an indifference curve also represents value. If we look up here at point A, here income is more abundant, but leisure is less abundant. And this is similar to what we had mentioned before. At this point, we don't have that much leisure, so its marginal utility would be higher than, say, at point B, where we have a lot of leisure. The marginal utility of extra leisure wouldn't be as much. So if, for example, we are at point B and we take away a fixed amount of leisure, we wouldn't have to give the person as much income to keep them equally as happy. But if they're at point A, leisure is much more valuable. We're at a lower level of it. Its marginal utility is higher. And so if we take away that same amount of leisure in order to keep the person equally happy, we would have to give them a much larger amount of income. Indifference curves for two people. So here, indifference curves can differ between people, and they will represent different things. So for example, if we look below here in the chart, in chart A, we have a steep indifference curve, okay? And in the second diagram, in B, we have a flat indifference curve. Now, a steep indifference curve represents, so when we draw a steep indifference curve, we're representing a person who places a high value on an extra hour of leisure. So they really like leisure compared to a person with a flat indifference curve. To see why, let's just think about taking away some income from either person, the same amount, and that's what these arrows represent, and then now thinking about, well, how much leisure do we need to give them to make them equally as happy? Well, this person A doesn't need as much leisure as the person in B. Okay, so you don't have to give as much income to make them indifferent, but B, this person places a low value on an extra hour of leisure. They would need much more leisure to make up for that fall in income. This person really loves leisure, right? So when you take away some income, you don't have to give them that much leisure and they'll be equally as happy. But this person over here, if you take away that same amount of income, they would need much more leisure to be equally happy. Okay, so we have these indifference curves which represent people's preferences, and people can have different preferences. Okay, so that's preferences. Now we must have a constraint. Okay, so we're going to talk about the budget constraint. This is also sometimes called the linear potential income constraint, and we'll talk about why it's called that in a moment. So it shows the combination of money income, or attainable consumption goods and services, and the hours of leisure per day that are possible or attainable for the individual. Okay? Basically, this is showing the trade-off between, working, getting money for consumption, and leisure. You need to give up leisure to work and earn a wage to buy consumption goods. And this is very easy to understand when we get to the diagram. Let's first just define a few terms. Okay, so in the linear potential income constraint, we have a variable yn, which represents non-labor income. Okay, so this could be property income, inheritance, lottery winnings. It could be a welfare payment. It could be social security payments. It could be a pension payment. W is the hourly wage rate. H is the number of hours allocated to the labor market. L is the hours of leisure per day. And capital T is total discretionary time. And of course, total discretionary time is the sum of the amount of hours you work plus the amount of hours of leisure. So someone's total income then, which is going to be on our vertical axis, is defined as the sum of W times H, so that's the hourly wage rate times the hours they're going to work in the labor market, plus whatever non-labor income they receive. So if non-labor income is equal to 0, then their income is simply just the wage times how much they work, W times H. Okay, so here's our diagram. So first, let's take a look at it without anything on it. So when we're looking at this model, we're looking at the income and leisure space. Okay, so leisure is on the horizontal axis, and income is on the vertical axis. T represents total discretionary time. Now, if someone has non-labor income, we're going to put that here on the vertical axis. So here, YN represents any non-labor income. And then when we go to the left of T, we're reducing leisure, and so we're increasing the number of hours worked. And so income is increasing, right? And so this line here is representing the wage times how much hours they're working, okay? And you can think about this intercept here on the vertical axis, this is going to represent if they took 0 leisure and so worked their entire discretionary time, it's going to represent how much income they're going to make. So that's simply going to be the wage times, this would actually be, capital T, because that would be all of their discretionary time plus their non-labor income. Okay? So if we think of W0 as a low wage, a higher wage would be represented by a line that's steeper and above. Okay? And that's because for each hour worked, or each hour, so in other words, another hour that leisure isn't taken, the amount of income is going to be higher because we're multiplying it by a higher wage. Okay, so the slope of this potential income constraint, or simply the budget constraint, is negative the wage. Okay? And again, sometimes we might get a bit confused. We're going to use leisure on the horizontal axis. And so when we increase leisure and go to the right, we are reducing hours worked. Hours worked increases from the right to the left. Okay, so at this point T, H is equal to 0. But as we move in this direction, H increases and T is falling. Let's go through a numerical example to clarify some things. So let's suppose we have a person. Their non-labor income is 100. Their wage is $10 per hour. And their total discretionary time is 16. Let's look at what their budget constraint would look like. Okay, so first of all, income is going to be determined by this simple equation, which is just the wage rate 10 times how many hours they work plus their non-labor income. Okay, and if we fill in values for different hours of work, we'll get this as a result. We'll get this as being the income. Here is the hours worked that we'll plug in, and this is the leisure hours. So if we plug H's into here, we'll get this far left column. Okay, and L here is just so you know that we can just keep track of how the hours of work and leisure change. So for example, if a person works 4 hours, then they must be taking 12 hours leisure time. If the person works 16 hours, well, then they have no time for leisure. because their total discretionary time, T, is equal to 16. So L is simply just 16 minus H. Okay, so if we were to plot this thing, we would have, first it's always good to look to see where T is. So T would be here at 16, okay? And we know at 16 the person isn't working. So what's their income? Income's measured on the vertical axis, so what's their income? Well, it can only possibly be their non-labor income, which we're told is 100. Okay, and so if we look over here, we have 100. Then as they start working, their income is going to increase by the wage times the hours worked. And that's where this line is coming from. And if they were to say, for example, work all 16 hours, well, what would their total income be? Well, it would be 16 times the wage rate, which is 10, so that would be 160, but then we would also add in our non-labor income, and we would end up with 260, and we can see that's where this point is here, just a little bit above 250 at 260. Okay, so that's a simple income constraint or budget constraint. That's how you would draw it and represent and be represented for this person who has simply a wage and a non-labor income. Here's another example. In this example, we're looking at a simple choice between full-time and part-time. So if this person does not work, so they're here, they would get a certain amount of non-labor income, YN, okay? But let's say they're only, they can only choose to work part-time or full-time. Well then, if they choose to work part-time, we're saying that this point here, B, would be their income for working part-time, and so that would be whatever number of hours that is multiplied by the wage. And if their other choice is only full-time, then that would be up here at point C, and that would be the income that they would get from whatever those full-time hours are multiplied by the wage. And then of course we always add in our non-labor income. Here's another typical linear potential income constraint or budget constraint. This is exactly the same as we saw before, but doesn't hurt to go over it again to reinforce it. So this is what a typical one would look like. We have a person with, if they have positive non-labor income, we're going to be somewhere on a non-zero portion of the vertical axis. Okay, so we mark off our non-labor income. And then we have a line here. Only if the person starts working, so we move to the left, so leisure is falling and hours of work is increasing, does income increase above this amount, and it increases by whatever the wage is. So a higher wage means a higher line because the wage is being multiplied, a higher wage is being multiplied by hours worked. In both cases here, we have hours of work changing or increasing, and in this case we're multiplying those hours worked by a lower wage, so the line's going to be lower, and this is multiplied by a higher wage, so the line is going to be larger. We could also have a nonlinear potential income constraint, and so the income could be some nonlinear function of hours worked. And in that case, we would have something that looks like this, or it could be any, it could be convex to the origin. We won't be covering or using this type of income constraint in the course, but just to let you know that we could use something like that if we had a reason to. Okay, so let's do some practice questions. So in this diagram here, we have two different indifference curves, one for Cindy and one for Mindy. And the question is true or false. Cindy must be offered higher wages than Mindy to work the same amount of hours. So is this true or false? So if Cindy must be offered higher wages to work the same amount of hours, which indifference curve would she, given to what we learned before, would it be a steep one or a flat one? Well, remember from before, we know that a steep indifference curve is for someone who really likes leisure. Okay, so Cindy is being represented here by a steep indifference curve. Well, it's steeper than Mindy's, and so then it must be Cindy who, relative to Mindy, would need to be offered more wages to work the same amount of hours because Cindy really likes leisure. Okay, so the answer is true. Second question. Consider a parent with $200 in non-labor income. She can earn $10 per hour working between 0 and 60 hours per week. Which diagram correctly reflects the potential income constraint faced by this working parent? Okay, I'll give you a few seconds to think about which one would be the answer. Okay, did you guess it? The answer is B. So here, this is our non-labor income. We're told that it's 200. Okay, so that makes sense. So if we look at all the diagrams, we know this one's wrong because it's not representing the 200 non-labor income. This one's only telling us it's 100. This one has a 200, but this diagram doesn't have non-labor income on here. This 200 here would be for the total amount of, so if this person took 0 leisure, it would be how much their income is. It would be 200. Well, we know that that's not true because in this question, the person has a $200 non-labor income, and if they worked all of their leisure hours, they would have much more than 200 because they're getting $10 per hour. So that's incorrect. So this one correctly represents it. So if this person worked all of their discretionary time, so their leisure is 0, they would get 60 hours times $10 per hour, which is 600. Okay, so this is correct, and the slope of this line is going to be -10, which is the wage. Now suppose that if this parent decides to work at all, then high quality daycare will cost a fixed $100 per week. Now, which diagram would reflect the due potential income constraint? So remember, this is based off the information from the last question. And so this person gets paid $10 per hour. They have a $200 non-labor income. But now we're saying that if they decide to work at all, they're going to have to pay $100 per week. So which diagram would correctly reflect this? So I'll give you a few seconds to think. Okay, so let's think about this. So if the person just worked a half an hour, say, we know that their income is going to drop by $100 because they're going to have to pay this fixed cost. Okay, so let's see which ones. So we don't really see any drop here. If this person, in A, if this person starts working and their leisure is being reduced, their income increases. So that's not consistent with a drop of $100. This one doesn't have any drop of $100. Now if we look at C, it does. So C, this is saying that if the person starts working, immediately their income drops by 100. So this is a good candidate. Same with this. If we work, if this is representing the person, it seems to be correct because as soon as they work, their income falls by 100. Now let's see. Okay, so now we have to think about which one of these two is correct. Well, here this is 200. So if the person just starts to work, maybe they work 10 minutes, they're going to get a little over 200. So something is wrong here. The person's non-labor income, if you remember, is 200, right? So this point here, corresponding to the top of this line, should be 200. And so when they start to work, it should go from 200 all the way to 100. And we can see then that D is the correct answer. Okay, next question. So suppose Bob's wage is W equals $16 per hour. His consumption and his non-labor income is $150 a day. He sleeps 7 hours a night, and the rest of his time can be allocated to working or leisure. What is the absolute value of the slope of his potential income constraint? Okay, so this one is easy. We're given some information that we don't exactly need to answer it. We know that the slope of the potential income constraint or budget constraint is negative the wage rate. And so the wage rate here is $16 per hour, and so the slope, the absolute value of the slope is 16. So the answer is C. Next question. Here we have the same information for Bob, but now we're asked what the maximum amount of potential income he can receive in 2 days. So what's the maximum potential amount of income he can receive in 2 days? Well, what is Bob's discretionary time? Well, it is 24 hours minus 7 hours that he sleeps. So he has 17 hours of discretionary time. And if he works that entire 17 hours, he will make 17 times 16, which is $272. Over 2 days, that's equal to $544. Now, is that the answer? Well, no, because we now need to add in the non-labor income, which is $150 a day for 2 days. And so the answer is 544 plus 300. And so our answer is 844. Okay, now we have a question that is asking us to calculate the size of the labor force. So we're given some information, some labor information for a particular country. We're told that the total population is 500. The population under 15 years of age or institutionalized is 120. We're told that 150 are not in the labor force, and we're told that there's 23 unemployed people. There are 10 part-time workers looking for full-time jobs. And it's asking us what is the size of the labor market. So we know that in order to calculate the labor force, we need to subtract from the total population the population under 15, so those who are not eligible to work. So we're going to take 500, subtract 120, and then we're going to subtract the remaining people who are not in the labor force, which is 150. Okay, and so the size of the labor force is going to be equal to 230. So it's 500 minus 120 minus 150. Next question. What is the unemployment rate? Well, we know the unemployment rate is the number of people unemployed divided by the labor force. And so here we know both of those figures. We know the number of people unemployed is 23, and we know that the labor force is 230. That's what we just calculated in A. And so what's the unemployment rate? The unemployment rate is 10%, which is just 23 divided by 230 times 100. Next question. Consider an individual with $5,000 of annual non-labor income. She has total available time of 80 hours per week, or 52 times 80, which is equal to 4,160 hours per year. So that's her, so big capital T is equal to 4160, right? That's what it's telling us. That's the total amount of discretionary time this person has. Their non-labor income is $5,000. Now we're told that her wage is $15 per hour, and then we're also told that she currently chooses to work 2,000 hours in a year. Okay, so now we're asked, draw a labor-leisure diagram, carefully illustrating her current labor supply decision. Okay, so let's do that. So we know we're in the income and leisure space. We know that T is equal to 4,160, so we'll indicate that there. Does she have any non-labor income? Yes, of course, it's 5,000. So we're going to draw a straight line up to 5,000 on the left here. So if she doesn't work, she's going to get $5,000 in non-labor income. If she starts working, she's going to make $15 per hour. If she works the entire 4,160 hours of discretionary time, should be at this point, and she would make $67,400, and that's obtained by multiplying 15 times 4,160, so that's how much money she's going to make working, and then we need to add the $5,000 in non-labor income. Okay, so this point would be $67,400, and if we connect those two lines, that is the budget constraint. The slope of this line is going to be -15, which is the wage, negative of the wage. And now it's asked, it wants us to represent the spot that she's choosing. So this is her current preference. We're told is 2,000 hours she's going to work. Okay, so in terms of leisure, that's going to be 4,160 minus 2,000, which is 2,160. So that means she's going to take 2,160 hours of leisure, and she's going to work 2,000 hours. And what would her income be if she does that? Well, it's going to be 2,000 times $15 an hour, and then we're going to add her non-labor income of 5,000. Okay, so that's the solution to the question. Now, next class, we're going to continue learning this model, but we're going to put preferences together with the budget constraint. And then we're going to look at the optimization problem that faces an individual. Thank you very much, and we'll see you next time.